Welcome to a quick video just going over some of the ideas for the chi-square test. A reminder that we are currently considering how different two populations are from one another and whether or not a population or a species has evolved from another species based on either allele frequency, genotype makeup, or some sort of evolutionary characteristic. And we know that populations can evolve through directional, stabilizing, and disruptive selections based on phenotypic and allele frequencies. And we looked at this population where we talked about an initial population or our predicted population and our observed population. Now, when we talk about two groups of data, two populations, before and after, predicted and observed, null and alternative hypothesis, we're really talking about their significance level, or how similar two things are to each other, and how similar do they have to be considered different. The general accepted rule is that for two things to be considered different, they need to have a 5% difference. And we do that by sort of measuring and standardizing the variance, or the difference between a predicted value and observed value, an initial population and a final population. What is their difference in terms of an x measurement or an x value? So I predict that it's going to be 0, and I look at my x-axis and it's a positive 0.4. The variance is 0.4 degrees. Now, categories are going to be the number of x variables that could occur within our experimental outcomes. X variables are just a way to consider what are the dependent variables. Are they categories? Are they numbers? Is it a grouping? It should be some sort of outcome that we're measuring a change in over time, or due to some measurement of change. Our null hypothesis is always going to be that there should be no difference between our expected results and our observed results. What do we predict and what do we see? If nothing happened and if nothing is causing something to change, then our predicted results should be always what we started off with or what we expected to see. Now, with this test, we're going to be determining the calculated value. The calculated value in a chi-square test is a standardized measurement of variance in our data. Basically, this is going to tell us, based on the X number of data points with this range of values and categories, this is how much variance we saw based on what we expected. And the critical value is going to be our standardized measurement. For this many data points, for this many categories, this should be the amount of variance that you see in order to say that two things are different. So let's do one. I have in here a Google Sheet that is set up to do a chi-square test based on the categories of p squared, 2pq, and q squared. And what we're going to do is we're going to look at a reindeer population in terms of its observed genotypic ratios, or the number of reindeer in generation 5. I am going to go to my no selective pressures in my data, and I'm going to do hair after round 5, 55, 38, and 7. These are the caribou that I see. Now, I need to make a decision. What is my expected genotype out of 100 that I would normally see? Well, I know that I have no natural selection in this model, which means that if nothing is causing alleles and genotypes to change, because there's an equal chance of passing on a big A or a little a, especially with a population that starts 100% at big A, little a, then I would probably expect to see roughly 25, 50, and 25 for my genotypic ratios. That's because a big A and a little a times a big A and a little a should give me 1/4 big A, 2/4 big A, little a, and 1/4 little a. And if that's the population after generation 1, and there's no selective pressures, then I would expect to see the same thing in generation 2, generation 3, and so on and so forth. If nothing should be causing my population to evolve, which is the null hypothesis, this is what we should see after 5 years. So let's take a look at our results. The O minus E, or the variance of our data points, is 30, 12, and 18. Now these two measurements where we take our variance and square it and then divide it by the expected is called a standardization of variance. And what that means is, in my first data point, I had a difference of 30. 55 minus 30. Now, I could also get that same level of variance by doing 2,530 minus 2,500. This is going to be a very, very small percent of those two numbers. Well, this variance is roughly 50% of my initial value. So the difference of 30 is really contextualized by what is my initial 2 points. A good way of thinking about this is, if your O minus E squared is significantly bigger than either of your 2 data points, then it probably means that there's a lot of variability in your model. If, however, I had this O minus E squared of 900 and I was comparing it to 500,000 and 500,030, I would be looking at, whoops, I had too many zeros. I would be looking at a level of variance that's pretty small relative to my 2 data points. So the last thing we do is we take O minus E and divide it by E, and we get these values. We sum them, 36 plus 2.88 plus 12.96, and we get our calculated value. If I look at a degrees of freedom table for chi-squared, I am going to be looking for my critical value with the information that the degrees of freedom are 2, because we always take the number of categories, 1, 2, 3, and subtract 1. And we're going to be looking for a significant value of 0.05. In order for my 2 value sets, observed and expected, to be considered different, they can only have 5% level of similarity. The significant the critical value for this is 5.91. What that means is my calculated value is bigger than my critical value. This tells me that my data set suggests that the alternative hypothesis is true. Now, my null hypothesis suggested that the genotypic ratio of caribou should be roughly 1/4, 1/2, and 1/4. The population didn't evolve. My alternative hypothesis suggests that the caribou population did evolve. The observed genotypes are a lot different than what I expected. But why? We didn't have mutations, so there was no way for new alleles to come in and change the genotypic ratios. We didn't have migrations. We didn't have new caribou come in any year. We didn't have natural selection in this model. That means that big and small hooves were no more favorable than the other. We also had random mating. We didn't have individual caribou strutting their stuff and saying, hey, I have big antlers, come mate with me. There was none of that behavior that we modeled. The one thing that we did, however, have was a small population, which means that over time, the observed ratios of p squared, 2pq, and q squared became more and more solidified based on just random occurrences of p's and q's mixing with 50-50%. It's very likely that out of 10 coin flips, I could get a 7 and a 3. And if that population, 7 and 3, then determined what my next generation might be, it might be 8 and 2, and then 9 and 1. This is called a reinforcing mechanism of evolution through a small population, which generally means that we see directional evolution occurring within the selective pressure of just small populations. I hope this has helped. If you still have questions, please see me.